Picture an offshore platform at 2 in the morning, hundreds of miles from the nearest coastline, completely cut off from the mainland grid. If the power dies here, everything stops. Production freezes, life support systems fail, and a multi-billion-dollar operation goes dark. The only thing standing between the crew and a total blackout is the prime mover, an aeroderivative gas turbine generator. Offshore engineering is a constant battle against weight and space limitations. You cannot note massive, heavy-duty industrial power plants on a rig that has to float or stand on steel legs. So engineers use jet engines, modified aircraft turbines, because they offer massive power in a highly compact, lightweight package. But relying on lightweight machinery in one of the most hostile environments on Earth means the platform's power grid is always walking a tightrope. The margin for error is razor thin. To understand why, look at the generator's manual. It might claim a maximum output of 15 megawatts, but that is the ISO rating, which only exists in a laboratory setting at sea level, exactly 15 degrees Celsius, with a perfectly clean engine. This chart shows what actually happens when you put that machine in the real world. Out on the water, the ambient temperature might be 35 degrees. Hot air is less dense, meaning less oxygen enters the compressor, which immediately strips away a huge chunk of the turbine's capacity to generate power. Then we have to subtract the parasitic losses. The air intake filters get clogged with salt and dirt. The heavy acoustic silencers on the exhaust restrict airflow. The speed-reducing gearbox adds mechanical friction. Very quickly, that pristine 15-megawatt machine is only capable of delivering 12. Before the crew even turns on a major piece of drilling equipment, the environment has forced the turbine to run hot and work close to its physical limits, just to keep the lights on and the baseline processes running. Then, the drill floor calls for the heavy machinery. They need to start a massive gas compressor motor, and they do it direct online, meaning they throw the switch and connect it straight to the grid without any gradual ramp-up. A motor of this size pulls an instantaneous, massive spike of current to overcome its own resting friction. Inside the generator, the magnetic field reacts to that current spike by aggressively biting into the spinning rotor. It acts like a massive invisible brake, instantly demanding a huge amount of mechanical torque from the driveshaft. On an isolated platform, a sudden electrical surge creates an immediate mechanical crisis, vibrating through the entire drivetrain of the gas turbine. In the very first fraction of a second after that motor starts, the turbine's control system hasn't even realized what's happening. The fuel valves haven't moved. The system is in an open-loop freefall. Look at this graph showing the electrical frequency. Because fuel hasn't increased, but torque demand has skyrocketed, the turbine shaft slows down. As it sags, the platform's grid frequency plummets. The only thing keeping the engine from stalling right then and there is inertia, the raw physical momentum of heavy steel components already spinning at thousands of revolutions per minute. Offshore grids prefer single-shaft turbines. Locking the compressor and power turbine together creates a unified rotating mass, which fights the sudden speed drop. But inertia only buys milliseconds. Momentum bleeds fast. The machine must actively fight back, or the grid dies. This is when the closed-loop speed governor finally wakes up. It detects the plummeting frequency and violently commands the fuel valves to swing wide open. A huge surge of combustible gas is dumped directly into the firing chamber, desperately trying to accelerate the shaft back up to its synchronous speed. But thermodynamics demands a toll. Generating that much immediate mechanical torque also generates a staggering amount of internal heat. This dual-axis chart tracks frequency and internal temperature. Because ambient air is hot and engine filters are choked, that sudden fuel surge acts like a blowtorch. The internal temperature spikes dangerously close to the metal's physical melting point. If the temperature crosses that upper trip limit, the turbine's self-preservation logic kicks in. It will instantly shut the machine down to stop the blades from melting, plunging the entire rig into a cold, dark blackout. To prevent that catastrophe, the platform relies on an automated brain, the power management system. It continuously watches the electrical terminals and the turbine's internal thermal sensors. In a fraction of a second, the system calculates the rising heat trajectory. It realizes the turbine is going to hit that temperature limit long before the massive gas compressor finishes its grueling startup phase. So, the computer triggers the platform's automated survival reflex, a process called load shedding. The system instantly executes a strict pre-programmed priority table. In milliseconds, it severs power to anything that isn't absolutely critical, shutting off the air conditioning, cutting the water injection pumps, and dropping the crew accommodations offline to instantly erase cumulative kilowatt load. Load shedding is a calculated amputation. The computer sacrifices the comfort of the crew and secondary processes entirely, just to ensure the core generator survives the hit. And it works. By shedding that extra weight, the total torque demand on the generator drops, the fuel valves pull back, and the internal temperature recedes from the red line, just as the massive compressor motor finally reaches full speed and settles down. Surviving a hit like that isn't luck. It is the result of incredibly precise split-second coordination between electrical load limits, mechanical thermodynamics, and digital control systems. The offshore generator sits at the fragile tail end of a volatile thermal system, a machine that must be meticulously managed to keep the platform alive and the fire burning.